Okay, we'll start our session 5. So since we're 33 minutes, so I'll do the session for until 45 or 50, and then stop the session and then resume after the break. Okay, so basically, for now we discussed about sequences and some basic real number systems and how they operate, but the thing is, even though, as I said, the real number system is the basis of analysis, it's not entirely true, which is because not only is real number important, but we have to know more about how our objects or sets are involved in our analysis. So in order to know more about the basic fundamentals of how sets operate and some properties of very interesting spaces, we need to know about basic property of some spaces or their qualities or some properties. And in a way, like knowing about this like basic property of a space, I think in mathematics that's called topology. So basically when you see like the term basic topology, it's basically about like learning more about the spaces and sets you're in. So like, because in mathematics there's a lot of sets and there are a lot of properties about sets and spaces. So knowing about them is very important, because if you're in some different space, whole terminology or sometimes or some concepts of things you're very used to like differs totally. So you have to be always make sure that what space you're in. So we'll be talking more about like these spaces before we go more on to like the function and some basic analysis courses, because we need to know about these topology courses. And usually like these parts are the part where students don't know much, because you know already a lot about like the application parts. That's why I'm not going to be like too thorough later on about differentiation and integration, because I already know you integrate and differentiate very well. So it's not a very important part, because you just can do it. And if you can't do it, you just sort to like Wolfram Alpha or you can just Google stuff. But like these basic understanding of like the fundamentals of analysis and like spaces is more something very hard to grasp at first eye. So I'm just explaining these in more detail. So if you have any question, please interrupt me and just ask me anytime. So because this part is going to be a little bit more challenging than the past courses. Okay, so again, another motivation, which is kind of hard to motivate for this session, but why topology? So why are we learning topology a bit? Because, as I say, we learned about real numbers because they are the fundamental objects that we use to do our mathematical logic. So most of our mathematical logic are going to be based upon objects which are real numbers. That's why we talk about real numbers, because they are like the objects objects we are playing with. And similarly, topology is about how these elements, so in R that would be like real numbers, right? In topology, we talk about how these elements relate to each other in some spaces. Like these real numbers have properties and some characteristics that we have to know about in order to make sure that we're not messing around with these numbers. So remember the concepts we have learned about in the past sessions about limits and sequences. I didn't talk too much about it in that sessions, but actually these concepts work well only if we first check what space we're in. Kind of like similar to like the limit one. Remember like in a rational number, because there's like whole limit doesn't work that well if the limit like converges to some real numbers, right? Something like this. So if you don't know about the space you're in and know about their properties, sometimes some spaces there are just using limits and sequences we are thinking is very problematic. Like just give you like very brief example that doesn't mean anything, so just listen to it and just forget about it. For example, you might be very familiar with a notion where limit is unique. So like when there's a limit, there's only one limit, right? But in some topological spaces, there are cases where there can be multiple limits. Something like this. So something like that, so there could be problematic if there's like a space where there's multiple limits. So we want to think about only spaces that are good. But if we want to know about that, we need to know about what these properties are. So we're just going to talk about those things briefly in topology. But since we do not have time, and we mostly deal with real numbers, thankfully, our works in topology will usually be in R. So we'll be talking about like just topology in R specifically most of the time. So don't be like too alarmed by the fact that we might be learning two abstract spaces. We're not going to do it much, although some concepts are abstract, but we'll try to focus more on R and try to think about more examples and exercises in R as well. Any question? Okay, so but we'll first talk a bit about functions because in topology also functional concept is very important. So now we're talking about functions, and in economics, functions is also very important because, well, I mean, we mostly deal with functions like production function, cost function, consumption function. They're all sort of functions, utility functions. So it's now time we learn about this concept of function and what it means actually. So you should already know what a function is, but I don't want you to keep on thinking of function as some sort of like a machine, you know, like the example of a machine where you just input something and some output comes out, some sort of like a machine concept. That is also like one part of a definition of a function, but that's not like the sole reason we use function. So function is actually more than that. It's like, as I wrote on the slide, so function is basically like a rule which we say we map one space to another. So for example, there's like a R space here and R space on the right. And what function does, it's like a bridge that maps one elements from the left side to the right side. So it's like connecting the bridge concept. You should understand function more like this. So basically, for example, the example where you have a function which is x plus 1. So if you think about it, it's like a rule that maps R to another R, right? So basically, you put R to real number such as 1, and it gives you 2, which is also a real number. So basically, it's a function that just maps real number to just real number in some new way with the new rules. So for each point in domain R, we're giving them some sort of rule and assigning them to a unique point in a codomain R. So now here comes why I said like sequence is a special sort of function. So if you think about it, sequence is just a special form of function where f comes from natural number to R. So let me talk about this. So you should already know this, but for example, like the sequences, you can think of it like this, like we write it like A1, A2, and 3. But if you think about it, this is just like a function in the sense that we just, let's say like A is a notation for function. Instead of writing this, just write it like this. And what you can see is this is like basically just a function that maps natural numbers to some real numbers, for example. So we can write this actually as a So function in a way is actually a special function where the domain is a natural number. So we're actually just making a function that maps natural number to some real values. So in a way, that's why I said sequence is just like a special type of function. So you should know that. So as I wrote, the index is natural number starting from 1 to infinity. So each of these points in the natural number, you're assigning them to some point in R. That's why I said it's a special case. Just a minute. Okay. All right. Okay, so we will talk about some limit of function now. So limit of function seems weird, but hopefully maybe some calculus courses sometimes talk about like limit of a function. So I hope you know some of this. But this is just similar to epsilon n concept we learned from the past part about sequences, right? But the only thing that changes is instead of using n, we use delta. So let me read the definition with you guys. So basically, when we say a limit of function, the definition is as follows. So we let fx to be a function, and we say that fx converges to fy when x goes to y. So this happens only when, for all epsilon, there's some delta such that if the absolute value of fy minus fx is smaller than epsilon, the absolute value between x and y is also smaller to delta. You can kind of see this is actually very similar to the concept of the sequences, except we're using like delta instead of using n. So this is like similar because basically when we say like fx convert to some value, what we're saying is that to that value there's some sort of interval again, which is epsilon. So there's some interval, and if we make the x value small enough, like close enough to y, we can get close enough so that the value is actually inside that interval. It's like basically the same thing. So like value again. Okay, let's draw like the XY graph again. Like, basically, let's say this is like the point Y, and let's say value of Y is like this. And what you have is like you will have an again you will have some interval, right? Something like maybe like this. So what this means is that there's some point X, and if X is very close to Y, such that like there's some, let's say there's like a delta now interval. There's like two intervals, right? Two intervals now. So if we get X close enough so that it is inside some interval that is in this interval, then the function, even though maybe it's like this, if you get close enough, it's going to be always, from this point, it's going to be always inside this interval, the function. So what this means is that it's very similar to the concept of sequence. The only difference is that as you get the value of an x very close to y, then in some interval, if the x goes inside this delta interval, the value of fx is going to be inside the interval of the epsilon. So it's, as it gets closer to y, the value becomes closer to the variable of value of fy. So I hope you understand this, but any question for this? So you can kind of see this is like very similar to sequences, except we're just doing this now. We're just making new intervals now. Because like function, there's no like sequence concept of going to infinity of an. So like all the analysis concepts are very similar. Like basically we're having this epsilon, very small epsilon, and we're just squeezing all these values inside these epsilon interval. So like a lot of the concepts are like similar. So you should get used to this kind of concept. So for every epsilon interval, we can choose some delta interval such that if x values are all inside this delta, the values of the function is going to be all inside the epsilon interval. So that's how we define the limit of a function. And can you kind of see the abuse of notation I used there? Anyone? Anyone who's familiar already with the limit concept, you might see there's some sort of, what you call it, some abuse of notation I just used here, which is that I wrote that there exists fy, but in limit concept, fy doesn't have to be defined, at least like in this case. So, which means like there might be no value for fy, but it gets closer to some value. So it kind of means like I'm kind of assuming continuity in this some point, but let me just not talk about this. But there's just a bit of an abuse of notation. So in case you're just like wondering about it, it's just why I just wrote it. Okay, we talked about some like brief introduction to the limit of functions because we will be using them a lot, especially in topology courses. And here are some like useful notation that you might use that will really make your life more useful. So we're going to assume that A and B are two sets, and we're going to let F be a function mapping A into B. So if E is like a subset of A, in case you don't know the notation, that E and A, there's a symbol between them that's a subset notation. It's like a set notation. So if E is a subset of A, then we define Fe to be the set of all elements of Fx. So what does this mean is that, let me stop the session after this, after I explain this. Okay, so like, let's say there's like an X, let's say like a set A, and what we're saying is that there's subset E, right? Like here. And let's say there's like some kind of function that maps A to some value here. Then what Fe means basically is like, you know, like all these points will have some points here, right? And you just kind of see what all these points, you just like group it all up, and this is Fe. So it's like basically it's a set of all elements of fx where the x is an element of E. It's kind of like it's like an extension of just having one value. So you just have a set, you just kind of see like where this set goes to. So that's what we define as FE. So we'll briefly stop here, and then after some 5-minute break, we'll resume. Okay, we'll resume the session. So we talked about basically what the first part where we said like if E is a subset of A, then we define FE to be set on all elements of X, where X is an element of E. We're kind of like seeing like where the subset of E lies in the codomain parts of the function. Just like it's very intuitive to understand it that way. And also, if we have a case where FA is B, we say that F maps A onto B. So you should know this. In Korean, what does this mean? 뭐라 그러죠? 한국말로 뭐죠? 이 언투가? 원투원은 1대1 대응인데 I'm trying to think about like how we say this in Korean. Okay, I don't know. So okay, I'm just gonna skip that. I don't remember. But there should be like a Korean name for it. But anyway, what does this mean is basically just like this. So remember that when we said like if we have a FE where E is a set, we're just seeing where the set lies in the codomain, right? So by saying FA, we're kind of seeing like where all the elements of the set in A is going to go in the codomain part. So we have A again, and here's a B. We say F is mapping A to B, and what that means is that all these elements is B, which means there's at least every element. So what this means is that if you pick any kind of element here, there's always going to be some point here where we can map this. This means like it's onto. Because like sometimes like there are a lot of functions where this doesn't work. So like sometimes there are cases where if you map FA, maybe it goes to a very small part like this. Like here. Then for these elements outside of these part, there will be no points where you can map this into here, right? So these kind of concepts are very important. So when we say that F maps A onto B, we mean that basically every element in B has some corresponding part in set A, where we can just map it in. So if that doesn't, and in a more general term where we also think about case where that does not happen, we just say like maps A into B. So in into case, we're not assuming that. But when you say onto, you're assuming that every element in B has a corresponding part element in set A. So just remember that notation. And also, the third one is also a very nice thing to remember. So we also have this inverse notation. So where if set E is a subset of B, we say F inverse E to be the set of all X in A, such as FXC. So this kind of sounds confusing. So I'll just kind of draw again to show how it works. So remember we have this again. So we had a part where basically I have a function here, but instead of having set E here, we're assuming some sort of set here, right? So we're having a set E here, like here. So what F inverse, we call this actually inverse image of E, to be more exact. So when we say this means that, you know, like if you do this, there are going to be some points where, like this, where there's some elements here where it's going to go into the inside the set E, right? And we think about all these sort of elements like that. And basically what we're doing is like, it's similar to like the FE part, but we're just doing it reverse. So we're just going like here. And this is going to be the inverse. So what this means is that the elements inside this blue part has some point, all has this element where the element goes inside this element. So set E. And this is kind of what we say the inverse image. Kind of get it because like FE is like the image of F, image of E here. Inverse image because it's going backward. So if you pick any point inside this blue circle, when you map it, the function is going to get it from here to inside the set E. It's a very nice notation to use because we'll be using it when you define continuity, actually, which we'll see how it works. And also something very important is this is actually this is different from the notation where you this is different from the notation inverse function. Just be aware. So this doesn't mean like the function is inverse. So it doesn't mean it's invertible. So like because usually you remember this inverse sign with an inverse function notation, but it's kind of different because inverse function is like it's a one-to-one function. So basically, there's a point. Well, we'll talk about it, but this is different because there are some cases where, in this case, there can be points where like here and here, and they can all go to the same point, like this. And still, it doesn't have a problem with that. We just get an inverse and you just include both of these points. So it's like different from the invertible function we are more used to. So keep in mind they're separate things. So they're not the same. And speaking of those kind of cases where like two elements going to the same element, we are talking about now about one-to-one function. So we also say that f is one-to-one. If that holds, kind of looks complicated, but just basically means what I said. So when we say a function is one-to-one, it just basically means there's no function like this. No function like going to the same element. Always one point goes to different element. And if there is a point that goes to the same element, that element has to be the same element. So if this goes to here and some element goes to here, that only happens only if that element is actually just this. So that's the definition of one-to-one. And I know this is in Korean. In Korean it means 1대1. So we say its function is 1대1. And when we say it's 1대1 function이라 하면은 we say it's one-to-one in English. So just remember that. Any questions till this point? No? All right. All right, let's move on. Why is that moving? Okay. Okay. Some also nice definitions that we need to know before we go on, because we'll be defining some concept in topology about size of a set. So we need to know what this means to be for a size. So sometimes we don't think about size of a set, which in mathematical term is all called cardinality of a set. But same thing, it just means the size of a set. And when we say size, it basically just means like the number of elements inside the set, like in a sense. So like for example, it's more easier to like compare in a finite number sets. Like set like this, like the size basically means like a number of elements. So in this case, it's like 3, right? And this one has just one element, so that's 1. So in a size term or cardinality terms, we can kind of say that this element is bigger, right? Has larger cardinality, I guess, right? So these kind of concepts called size of a set. So interesting thing is function. As I said, do you remember like saying like function is not just like a machine where you just input things and output comes out. There's actually something more than that. And one of them was that it maps between spaces. And what it means is that basically, actually function can be used to compare sizes of two sets. For example, like, let me just use the finite case again. Let's say this part set is actually just like a 1 to 3 element. There's a 1 element, 2 element, 3 element. And codomain part let's say there's like a 4 element. 1, 2, 3, 4, right? So we can think about like a function where we map one element to just one unique element. It's like this. There's a function, and you can just go like this. Then you can see like the function is not onto, because there's a function. There's a set B where there's a number 4 where there's just no element we can use to map it to. But in a way, because we show this, we kind of use the function to kind of say implicitly that this function, this set has larger size, right? Because we mapped it by mapping it just like to one unique object to one unique object. And what we did, we showed that this is not onto, which means there's some element that we cannot just map uniquely. If you want to map this, we have to go something like this, which is impossible. So what this means is that we can kind of show by using function, we can use it to compare sizes of two sets, right? That's why it's frequently used. And the problem is, why bother do this thing? I mean, at least in the finite set, why are you doing this? And we can even see clearly that this is 3 and this is 4. Why are you using function to like kind of show and compare sizes? And this is not because functions are like useful in comparing sizes in like finite sets. The problem occurs when you're trying to compare infinite sets. So like, for example, think about it. Like, this is easy. And I don't think you don't need to have a function to do this, like to show that this is bigger. Well, for example, think about this. What about set of all natural numbers and set of rational numbers? What is bigger? Can you count the natural numbers and rational numbers? I mean, you can try, maybe. I don't know. I've never tried it, but 못 세겠죠? 기본적으로. 참고로 어떤 게 더 클 것 같아요? 아시는 분이 있을 것 같으니까 아시는 분은 말씀하지 마시고. N이랑 Q 중에 어떤 게 더 클까요? Which one is bigger? What do you think? Any suggestions? There's no. 네. 내셔널이 더 크다. 그럴 수도 있죠. 근데 이제 네네 아닌가요? 죄송해요. 제가 내추럴 넘버 잘못 들었어요. 레저 넘버 더 크다. 그쵸? 약간 그래 보이긴 하죠. But like the problem is we can only make very guesses because I mean in the sense they're both infinite. Natural numbers are infinite numbers and Q is also infinite numbers. We can't count them to check which one's bigger. That's where the function is very useful because instead of explicitly counting the size, we can actually define the function that maps one-to-one and onto function between two sets. And we can say that if the function is not one-to-one, then it kind of shows like this part is bigger. So for example, in this case, if you want to show that this is bigger, maybe you can make a function that maps from n to q. And if that function, maybe if it's not onto, that'll mean q is bigger, right? Something like this. So that's where like the function is very useful in comparing sets of infinite numbers. And I don't remember if I put about the part about the sizes between these two numbers. We'll talk a little bit about it maybe in the end. But before we go into it, we need some more definition about cardinality of a set and what it means to have a size and some notation for infinite sizes. Okay. So some notations. You see like the curly symbol there? Like, I don't know how to pronounce it, but let's just say it's curly notation. So A curly B basically means we can define one-to-one function from A onto B. Remember that when we say there's a function one-to-one from A onto B, that basically means that two elements have same numbers in a sense, right? Because like 1 to 3 and 1 to 3. You just map 1 to 1, 2 to 2, 3 to 3. That's a one-to-one function that is onto. So when you have a function between two spaces that is one-to-one and onto, we say that that sets are of same size. That's like a definition. And we define A set A to be finite if A is curly to A is equivalent, actually we kind of say equivalent to, so if A is equivalent to these sort of finite number of sets, right? Think about it, because if A is of same size to some number of natural numbers where the natural number is finite, so ends at some endpoint, right? That would mean that the set has to be finite. It's kind of like in a way it's like a sequence, right? If you remember sequences, as long as like a sequence, you're just mapping like sequence to some values. And if that sequence ends in some finite term, we're saying that this set is actually just finite set. That's how we do it. And of course, infinite is very easy to define. We just say A is infinite if it's not finite. So if we can't do that, so if we can like make some set A equivalent to some 1 to some n, finite n, we just say that it's infinite. And this is just a bit of a very confusing term here. Let me just see if I did. Oh, I did it. Okay. And there's some weird thing going on here, because like we've already defined infinity, right? Then it should end, right? Because there's nothing more than just saying a set is infinite. What more there is to say? But unfortunately, mathematicians have found out that actually infinite can mean two things. And here it comes. The first one is we say A is countable if A is equivalent to natural number. So you can see that countable is a form of infinite, right? Because basically what you're saying is that the set A has a one-to-one function onto the natural number, and because natural number is an infinite number, right? So it's infinite number. So the size of the set A is infinite. But we say that that size, that infinite set, is actually countable when we say A is equivalent to the natural number. You might think like, why bother making two different definitions if we're saying the same infinity? But we'll see how it goes out. So just bear it with me. So we say that it's countable. Well, I mean, think of it like intuitively. Think of it like, natural numbers. You kind of use it to count numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. So like intuitively, so we can count it. I guess it's infinite, but we can count it. And there's this thing called uncountable. That is, sometimes we say the set A is the size is uncountable if A is neither finite nor countable. So this is a very weird point, because we kind of said already that. Let me just draw this like a diagram. So basically, in our like naive understanding, the size of sets should be just two things, right? Just like finite, there should be like finite number, and there should be just infinite number, where the finite number will have some points like 1, 2, 3, 3.45, some these kind of sets, right? All these sets that have finite number, and infinite should be like the same old n, q, integer, and some other infinite numbers, right? Sets. And we think like the categorization should end here. But interestingly, for infinity, mathematicians have another new subdivision, which is called countable and uncountable. And it's like, for example, I didn't write R, right? There's also real number. So basically, like the infinity is divided into some sort of countable and like uncountable, right? But there's this like new subdivision inside infinity. And we're going to see why this happens and why this is a needed concept. Because we think like they're all infinite. Why are we dividing infinite sets? So basically that's why we're going to talk about it. And just for useful notation, some of the textbooks, when you say like A is at most countable, it usually means like A is finite or countable. Usually. This is like the beautiful notation. Some textbooks actually go like at most count. Some textbooks, when they say like countable, it actually means at most countable sometimes. So just like have to like make sure which definition the book is using. But mostly, like to be more strict, like we should say at most countable, which means it's finite or countable. So, you might wonder, why we are having like this kind of two subdivision of infinity concept, because we think they're all infinite number of sets. And that's because it's kind of hard to grasp this meaning, but there's actually two levels of infinity. It's like, it could be like mind-blowing for people who didn't know this, but there are two levels of infinity in this world. So you might, as I wrote in the slide, you might wonder, what is this countable infinity and uncountable infinity? What does it mean when something is countable and something is uncountable? So surprisingly, as I wrote, in terms of a cardinality or the size of a set, there are two levels of infinity. They are both infinite, but there's like levels. 급이 있는 거죠. So in intuitive sense, uncountable is a bigger infinity than countable infinity. So example of an uncountable set is R actually. On the other hand, N, Q, and I didn't write it here, but integers, set of all integers are all countable. I didn't write like too much about what this means and like a deeper understanding of it. So more reference, you can check the root in PMA book. But what this kind of shows is that it's very interesting in a sense that, as some of you point out, there's like a gap between size of a set. So actually, although we think like maybe rational numbers bigger than natural numbers, the thing is actually natural numbers and integers and rational numbers, they are all same size. They're all countable. But it's like a gap. Real number is uncountable. So what this means is that real number actually is a bigger infinite number. Although it's kind of hard to intuitively understand what it means to be bigger infinite, but it's like that, so interestingly. So unlike other elements, R is a bigger infinity. So I didn't wrote it like here, but you can make like a function where the function will have like one-to-one onto function between these elements. But you can't make a function that has a one-to-one onto here. It kind of shows that actually R is a bigger element. So there's a two levels of infinity that comes into play. Right. I just wrote down some useful properties of countable and uncountable infinity because they could be very confusing. So the first one is, I didn't write the proof, so I think it's a bit of a waste of time to try to write down all the proofs here, so I just wrote it here. So some nice property. First one is, every infinite subset of a countable set is countable. It's just kinda intuitive. So what this means that you cannot get like bigger sets out of countable sets, of course. What it means like, if there's a countable set, its infinite subset is always going to be countable. It's kind of intuitive, right? You're not getting more bigger sets out of it. You're not going to get like uncountable set out of a subset of a countable set. So that's how it works. So, and the second notation is, and the second one is actually very important because it's used a lot, and you might use this sometimes, which is countable union of countable sets is countable. So what does this mean? So, like countable sets, even if you like union them, if you like group them together by countable sets, they're still countable. But what this means is that, for example, let's say there's some number of sets where like an, let's say there are like all sets of countable numbers, and by meaning a countable union of countable sets, what we're doing is, because an's are all countable, we're kind of making a union for all n, like this. And this is still countable, which kind of shows that there's like a very big gap between countable and uncountable. So basically, even if you try to make countable sets into uncountable, even if you make countable unions, it's not going to be uncountable. So it kind of shows that as long as there's like a countable union of countable sets, it's not going to become some uncountable sets. So it's a very nice one. It's like. And I'll give you some exercise before we go into metric space. So remember the term countable union of countable sets is countable, right? I'll give you some very like quick exercise I just kind of thought of, which is like this. So you can use this actually to solve a question. For example, okay, note that, remember that real number, it has rational part, and I'll denote I as irrational numbers. So this is like root 2, right? Remember this? Can you show that I is uncountable? Prove it. And I'll, about 5-6 minutes, I'll pinpoint just one person to see if he can do it. But I mean, if you can't do it, it's fine, but I'll give you some 5 minutes to solve this. But the tip is use the thing called countable union of countable set is countable. So we're trying to prove that the set of irrational numbers is actually uncountable. 하고 싶은 부분 있으신가요? Anyone want to try? Or if there's no one, I'll just pinpoint one. So, no one? Okay. Then 오늘 한번 이쪽에서 한번 해보시겠어요? 네네네. 오셔서. 네네. 맞으면 더 좋고 안 맞으면 상관없고요. 있는 건 아니니까.
아이를 카운터블이라고 가정을 하면 그러면 두 번째 거에 의해서 이게 뭐니까 그럼 얘가 카운터블이 돼야 되는데 근데 우리는 이 리얼 넘버가 언카운터블이라는 것을 알기 때문에 그래서 이 명제는
그쵸.
틀린 게 돼서 결론적으로 i가 언카운터블이라고
하다. 그쵸.
생각했어요.
너무 잘하셨는데요? 프로모션도 있는 것 같은데. 아닐까요? 너무 잘하시는데요? 네, 맞아요. 이렇게 풀면 됩니다. So you just have to solve it like this. So, what he said is exactly correct. So basically what we're doing is, I'm not sure if Mike's going to work here, but, so we're proving that irrational number is uncountable. So this is actually a very nice exercise where you can use proof by contradiction. So just kind of show, first assume that like, because we're going to prove that this is uncountable, assume that I is countable. Then drive like a contradiction out of it, which is, because we know that Q is countable and R is uncountable, because we know that countable union of countable sets is countable. And when we say countable, it means it includes the finite union. So basically, so if we union the irrational number with irrational number, it's going to have to give us countable set. But by definition, Q union I is real number. But that would mean that we're saying that R is a countable number, which is a contradiction because R is uncountable. So, because this goes to contradiction, this means that the assumption was false. So I has to be uncountable. That's how we put it. Like, very nice question where you can prove it using proof by contradiction and some of the things you learned in class. So I thought it was a very nice example for it, use. Okay, let's move on. Okay. I'm recording. Okay. Oh, okay. Oh, I just remembered that I didn't do the third one. So, third one is also a very interesting part. So, set of all sequences whose elements are the digits 0 and 1 is uncountable. So, what does this mean? It's just like, remember like elements were, it's like, elements like the binary numbers. Or think about like a set of all points where it's like, it's either 0 or 1. There could be like 0, 0, there could be like 0, 0, 0, 0. And there could be like a 0, 1, 0, 0, 0, 0. And 0, 0, 1, 1, 0, 0, 0, right? All these sort of, set of all these number sequences where sequences or decimal points, it doesn't really matter, where it could be either 0 or 1. You might think this is small because the elements you can have is only just like 0, 1. But if you all combine these and make a set, it's uncountable. So, very nice thing you can know about. Actually, these sort of one are actually the way we kind of use to show that R is uncountable. There's a way that you use this to prove something, but I'm not going to go too much in detail. All right, so we talked about the size of a set. We talked about countable, uncountable, infinity, and infinite set. Now we're going to go on to more about the property of a set itself by making things a bit more abstract, unfortunately. But it's not that different from the space we were dealing with. It's just the same space with just a bit more general names. So these actually, for example, like we're talking about metric space, right? But actually R is a metric space, usually. So just don't be like too alarmed by this weird word. It's just like same thing, but we're just like making a more general notation to use. So we'll be defining some properties of the space that we're going to play with. To do that, we have to generally define first the space that has a distance. So remember R, like R has a distance, right? At least like usual sense of R, because we kind of intuitively remember if you have value 1 or 5, you divide, not divide, you subtract 5 to 1, you get 4, right? And you kind of think of it as like a distance, like in a horizontal sense, like there's like a distance here. And you kind of measure distance by subtracting both terms, right? And actually, this kind of distance concept is very important. Nice concept. That's why you usually denote space that has a distance concept as metric space. So whenever you see like metric space, it's basically like a space where some sort of distance concept is defined. You're defining some distance. So let me just read like the rigorous definition of metric space. So we always have a set X. And sometimes the elements of set X, we call them like points. Or you can just call them elements, but I'll just call them points from now on. So these points, so they have a point. So there's a set X. We say set X is a metric space if for any points P and Q of X, there is some real number which is denoted by dpq called distance from P to Q, such that these properties hold. So what does this mean? It's like basically what it means is that we're just defining distance. Do you see like the D symbol there? Like it kind of sounds weird. But what we're basically doing is because we have a P and Q, right? What we're saying is that for any P and Q element in X, we're defining like a distance between them. So it's like these like actually you can kind of think of D as a distance. So for any P and Q, we're making some kind of distance concept between two elements. And then they have to do this. And this is actually in R term, this is very intuitive because think about it, like what this is saying, like the first A part, it says like two elements, their distance is bigger than 0 if they're not the same, which is also happens in R, right? Like if For example, think about 2 and 1. As long as these two elements are different, if you subtract them, you always get positive distance. But what this says when it says dpp is 0, this means like if the elements are the same. Remember in R, if you subtract same element, you get 0, right? So but what this is saying is actually just like saying like general concept of distance. So as long as two elements are different, you're going to get some positive distance from them. And if the elements are the same, you get 0 distance because they're the same object. And number B is also very intuitive. What it's meaning is that the distance between two elements, they're same even if you switch them. You know, like, remember like I did this, but actually like distance between two elements, we use absolute number, right? So even if you do this, or we do -1 from 1 minus 2, they all get same number 1, right? So what this is saying is that even if you switch two elements, the distance between two doesn't change. Because, I mean, basically, this distance is a positive concept, right? It's an absolute value concept. So that's what number B is saying. And number C is I'm not sure, but I think in English, I think it's also called triangle inequality concept. So what it means is that dpq is smaller than or equal to dpr plus drq. It's kind of complicated. What this kind of means is just that this like, for any elements, it's like, let's say there's like a 1, 2, and 3. So what this in real number term, what this means like triangle inequality, where let's say it's p qr maybe. So what this means is that if you just divide the distance, this is 2, this is 1, this is 1, right? Plus it, you get 2, right? It always has to be bigger than, greater than, or equal to this, which is, in a real number sense, a lot of time it's called triangular inequality, triangle inequality, something like that. It's a very useful concept, and it's also defined in the distance concept and basically what this is just like a special, we're just making like distance concept in R to be more general and just defining it to be metric. Because the reason we kind of use this is because distance, you can actually define them in a very different way. For example, like right now, we're like the usual definition of distance in R is just subtracting them, right? But what we can do is actually, instead of doing this, like it doesn't mean anything, but instead of doing this, we can define distance as like this. Like subtract them first. Oh, sorry. You define distance like subtract them first. Let's say like, and then add 5. And we'll say this is like distance between two elements. And then the number changes, but it's still the distance. So it's like, it doesn't matter like what number you're assigning to the distance, as long as you have the constant distance. It doesn't matter if you just add 5 or add 100 after something. It's like, it's just another way to define distance between objects. So as long as you kind of do whatever you want, we're just trying to define more general concept distances. So distance, you can name it actually different ways. But in R, we usually use the absolute value as a distance. All right, and I also wrote that on the bottom. We can easily see that for a usual space in real number, this distance function is just p minus q absolute value. So basically, it's just saying that. So, and I wrote this like whole lot of definition about metric spaces and some exercises. So I'm not sure if I'll be able to finish all of this right now, but let me try it. And if I go past like 45, 50, I'll end the session and we'll go for lunch break. Okay, so there are some properties of a point in metric space. So now we're talking about, so we define the metric space, especially like a general space for the distance. And we're going to see what kind of properties it have for elements inside them, because we want to talk more about these elements. So first we have some definition where we're going to use A, set A, which is like a subset of X, and X is going to be the metric space, and we assume that X is a point in A. So like, you know, X, there's an X. So like X is like the big playground, like this. It's like whole space. It's a metric space, so it has a distance constant. And A is some sort of subset here, and there's like an X. Just remember the situation. So we have like this kind of situation. And we're going to see some sort of properties here. We again have epsilon, our nice friend. So we have an epsilon, some positive epsilon, and we define epsilon open ball of X as this. So what the heck does this mean? So if you closely look at the definition, what you can see is that basically the open ball, epsilon open ball, is at basically set of all elements where the distance is smaller than epsilon. See? So X epsilon, so X and epsilon are fixed. And we're thinking of set of all elements where distance is smaller from X by epsilon. So graphically what we're doing is, let's say the distance is like this. So epsilon is like about this big. This is epsilon, right? 보이시나요 혹시? 작나? 작을 수 있을 것 같긴 한데. Let's say this is epsilon. So this is a distance, epsilon distance. So by open ball, it's very intuitive. What it means is like it's like this. So all these elements here, they're going to be the distance from them from X is smaller than epsilon. So we're just like getting all these sets. And because in two-dimensional sense, it's like a ball, right? Just draw like a circle for the distance. So basically, that's why we call this epsilon open ball. Although we say open ball, sometimes due to some constraints, like they're not ball, like in graphical term, but still, it's very intuitive in the sense that it's basically like set of all elements that is there's a set of all elements where the distance from X is smaller than epsilon. So that's how it is. So that's open ball. And we say that X is an interior point of A if there exists some epsilon where the open ball goes inside the set A. So what does this mean? Remember we draw the open ball? Because we can think of any epsilon that is positive. Instead of drawing this kind of ball, we can draw like bigger ball, for example. Like, let's say like epsilon is like this big. And we can draw something like this. Although like you can't go out X, but like this, right? Or maybe you can use smaller epsilon. Maybe epsilon is like this small. And you say go like here. But when we say that X is an interior point of A, what we're saying is that we can find some epsilon where if you choose the epsilon, all these sets are inside A. So because in this case, for example, if we can find some open ball like this, and this goes inside the set A, we say this X point is an interior point of A, right? And you know, like these open balls, they don't go inside A, right? So if there's only elements like this, you can't say X is an interior point. But as long as you can find some epsilon like this, we're saying that X is an interior point. You might think this is very obvious because you think like, doesn't like X then always doesn't like every element have like interior points? Because you can like make it very small. But then the problem kind of comes out when you have points like this. For example, think about like a point at the boundary, like here, right? Then you can kind of see that this is not going to be an interior point because even if you make epsilon really small, very small, like this, it's always going to go outside the set A. So it's never going to be an interior point. So these points, because they're inside here, we can make some small epsilon so that it goes inside A. And this holds for almost every element as long as it's not in the boundary. So even if you go like this small, like the point is like very close to the boundary but it's not on the boundary, then I can't draw it, but you can make a very microscopic small epsilon that just goes inside here, then still that's an interior point. But as soon as you go to the boundary, you start going outside the set A. That's why we say some elements are not interior point and some elements are interior points. And by definition, we write it so like this. So x is interior point if we say there exists some epsilon that is positive integer such that there's a ball we can squeeze inside the set A. So that's how it is. Any questions? If there's no question, we'll stop here and we'll have some short lunch break and we'll start at 1 p.m.